Okay, so to calculate a function value f of 7 means find the output when the input is 7. The input is x, so we want to figure out what the output of this function is when x is 7. So easiest way to do that is change every x you see to a 7. So -3, whoops, I hate it when it does that. Moves right in the middle of me writing. -3, 7 minus 2 plus 5. So I took this function right here, and everywhere I saw an x, I changed it to a 7. Okay. Order of operations. We need to do grouping first. Grouping is parentheses or any other kind of grouping. Absolute value is grouping. The 7 minus 2 is grouped together inside the absolute value. So we're going to have to do that first. So 7 minus 2 is 5. So this now gives us -3 times the absolute value of 5 and then plus 5. Okay? Absolute value. Absolute value means the distance from 0. So how far is 5 from 0 on a number line? Well, it's 5. In fact, absolute value is the same number that's on the inside. Unless the number is negative, then you just make it positive. So when we do our multiplication, which is our next step, we're really just going to be multiplying -3 times 5 because the 5 is already positive. So -3 times 5, which gives me -15, and then plus 5. So my final output here is -10. Okay. Second one, we are going to take g of x, which is right here, and we are going to substitute in a -4. So -4 substituted in to g of x. So I'm going to replace every x with a -4. So g, parentheses, -4. We read that g of -4 equals -3 times -4 squared minus 5. So I put the -4 in here and in here because those are where the two places in my function that we had the x's. So the x's are gone. They're replaced with -4. Order of operations. There's really no grouping here unless you count the -4. The -4 just means make the 4 negative. So that's the only grouping. But we do have to do exponents after grouping. So we're going to start by doing -4 squared. Now, notice that it's the 4 that's squared, but it's also the negative. So we're squaring the entire -4. That means -4 times -4, which is positive 16. When you square a number, it will be positive. Okay, you need to put that -4 in parentheses to make sure that you're squaring the entire number, the negative and the 4. So now we do multiplication. So we're going to do -3 times 16, which is going to be -48, minus 5, which gives us -53. And there's our final answer, our output. Okay. Down here, we want to find the equation of a line that passes through 2 points. To do that, we need y equals mx plus b. We need to figure out m, which is the slope, and we got to figure out b. So there are two things that we need to figure out on the second problem. We got to figure out what the slope is between these 2 points, and we got to figure out what the y-intercept is. Now there is a graph grid here, because yes, you could graph these 2 points, draw the slope triangle, and figure out the slope that way. And nothing wrong with doing that. However, I do want to make sure that we are comfortable finding slope when you don't have access to a nice graph grid, because a lot of times that is the case. You might not have access to a graph grid, whereas you usually have access to some type of piece of paper. So this doesn't require a graph grid. This just requires something to write on. So my slope is the change in the y's divided by the change in the x's, or rise over run. So we go to the y's, and we say, hey, look, my y's changed. They went from -3 to 5. That is an increase. They went up. And if you count it, they went up by 8. And I go over to my x's. And I realize those changed as well. They went from -5 to +3. That is also an increase of 8. So my slope, delta y divided by delta x, is 8 over 8, or just 1. So check, got my slope. I now need to figure out the y-intercept. The way that we do that, using the equation, is we take our slope. I'm going to put that in for m. We take one of these 2 points. Doesn't matter which one. Most people would probably choose 3, 5 because they're positive values, but it does not matter. So that's what I'm going to do. I'm going to use 3, 5. 3 is my x, 5 is my y, and then that's my slope. So let's put it all in there. Y is 5 equals m is my slope. X is 3 plus b. That's going to allow me to solve for b. So 5 equals 1 times 3 is 3 plus b. Subtract 3, and b is 2 because 3 plus 2 is 5. So now I've got my b. So now I know what the equation is. I write it all out. Y equals 1x plus 2. The 1 in front of the x is optional, so if you just write x plus 2, that's fine. And there is the equation. And then the last question is -2, 4, a point on that line. If it is, this equation has to work. In other words, if I take the x and add 2, I should get the y that's here. If I don't, then it's not a point on the line. So let's check it. The y is 4. The x is -2, and then plus 2. So if this is true, then the answer is yes. If this is false, the answer is no. So is this true? Say -2 plus 2. Is that equal to 4? Nope. -2 plus 2 is 0. That is false. So -2, 4 is not on the line. And again, of course, graph grid, you could graph the line and physically see if -2, 4 is on the line by literally graphing it and checking. But this is how you would do it without a graph. You just plug in the values for x and y and see whether or not it comes out true. Okay, so yesterday we took an ESA on systems. So hopefully you have seen your score posted on Schoology and also looked at the solutions in Delta Math. The solutions were published yesterday at 3 o'clock. So if you go to Delta Math and look at your test, on the upper right-hand corner on the top, it'll say Show Solutions, and it'll show you exactly which ones you did wrong and show you the correct solutions to those. Test corrections. Unless you got 100% on the test, and there were several that did, but unless you got 100% on the test, you will also see that there is an assignment for test corrections. Delta Math now upgraded, and they automatically create the test corrections for you. So you no longer have to go in and say, I lost 1 point on this problem, 2 points on this problem, and you don't have to do all of that. Just go right to where it says test corrections, click the green button that says initialize, and boom, your test corrections are created for you, and you can start working on them. Okay, so if you want to do test corrections, you passed the ESA, but you want to increase your score, test corrections are due next Sunday. So not this Sunday in like 3 days, but the next Sunday of next week. And you can earn 30% back of the points that you missed. If you did not pass the ESA, then test corrections are no longer optional. You must have them done before you can retake the ESA, because if you didn't pass, you do need to retake. So we have 2 weeks from tomorrow is the end of the semester. If you need to do retakes, whether it's on functions, linear relationships, or systems, you need to make sure you've got a plan in place to get whatever retakes you have to do, whether it's 1 or 2 or even 3, taken care of in the next 2 weeks. 2 weeks from tomorrow is the end of the semester, so that's basically, not including today, 11 class periods, 11 school days. If you count the weekends, it's like 15 days till the end of the semester, okay? Everything that you guys want to have counted for the semester needs to be done by March 26th. So any late work that you want to do, Delta Math will go away on March 26th at midnight. So like all those assignments that says late work available, late credit available, those will now say no credit available. They'll still be there. You can look at them, but you won't be able to get any credit after March 26th. So you need to get everything done by March 26th that you want to do in order to have the grade that you want. If you want to have a grade, you have to pass all the ESAs. So that includes retaking any ESA that you are below 70% on. So that is non-negotiable. In other words, if you have any missing ESAs on March 26th, you will not have a grade. It'll say no credit on your transcript, okay? So make sure that if that applies to you, talk to me. When are you going to do your retake? Come in after 4th period, on some kind of regular basis for the next 2 weeks, and I'm happy to help you learn the topic so that you can pass your ESAs, okay? But in the meantime, we are going to start Chapter 4. We will not have an ESA on Chapter 4 that will count for this semester. I think we will get to it and take it like on the very last day, just so that we don't have to hold it over after spring break, but it's not going to count for this semester. It'll count for next semester. However, all the stuff that you turn in the next 2 weeks will count. So like Delta Math assignments and notes and all of that. So Chapter 4 is on sequences. This is kind of a fun chapter, because what is a sequence? It's a numerical pattern of values. So it's really all about pattern recognition. That's what creates a sequence. So we can use a letter, for example, A, and define a sequence. A sequence is a pattern of numbers. So right here, sequence A is 1, 3, 5, 7, ... means it keeps going. So you'll look at those first 4 numbers and you try to see what the pattern is, what's going on, so that we can say, hey, what are the next 2 terms? And you guys see what the next 2 numbers are? Yeah? If I told you that they were 9 and 11, are we good with that? Okay. And why? What are we doing here? To get the next number, if you take a look here, we're just adding 2. So add 2 to previous term. The numbers are called terms. Previous term. Except I have my glasses on. Previous. I did spell it right. I wasn't sure I did because I couldn't actually see what I wrote. Okay, so that is a sequence generated by adding 2 to the previous term. Sequence B, 2, 4, 8, 16, 32. This is not adding 2. It starts off that way, 2 plus 2 is 4, but then it falls apart because adding 2, you don't get 8. Adding 2 to 8, you don't get 16. So, what's going on here? Yeah, we're doubling. So, multiply by 2, multiply by 2, multiply by 2, multiply by 2. That'll give me 64 and 128 as the next 2 terms. So instead of adding 2, we multiply by 2 to get the next term. So what are we doing? We're just multiplying by 2. So you just double whatever number you see, that gets you the next number. So again, it's pattern recognition. Sequence C is a little trickier. So take a look at sequence C and see if we can figure that one out. I'm going to tell you the next term is 27. Yeah. Yes. Okay. After 27, the next one is 38. Anyone see what's going on? Yeah, Cameron?
They add 1, then add 3, so I think they're adding 2 every single time, or like multiplying and adding 2.
Okay, so he says, look, to get from 2 to 3, you added 1, right? And then how do you get from 3 to 6? Add 3. How do you get from 6 to 11? Add 5. So we're changing the number we are adding, but there's a pattern in the numbers we're adding. To get from 11 to 18, we add 7. So from 18, I then added 9. And then I added 11. And then I would add 13, and then I would add 15. So we could say, how is this generated? We could say we are adding consecutive. Consecutive is a fancy word for the next odd number. I'm going to say odd integer, because we're not doing decimals or anything. Integers just means whole numbers. So we're adding consecutive odd integers. So we add 1, and then the next odd number is 3, and then the next odd number is 5, and then the next odd number is 7. So we're just adding the next odd number each time. Okay, sequence T. 10, 7, 4, 1. You can hopefully see that this one is decreasing. You guys see what's going on here? Yeah. What's next? -2. And then -5. So we are decreasing. And we are decreasing by the same number every time. Take a look. We're just subtracting 3. So subtract 3 each time. Another way of saying this, instead of subtract 3, we could say add -3. So you could say we're subtracting 3, which is absolutely true, but you could also say we're adding -3, because adding a negative is the same as subtracting. This is the exact same one, so obviously we're not going to do that one again. We're going to move on to page 2, though. Okay. An arithmetic sequence. There are actually 2 types of sequences that we're going to focus on in this chapter. And the first one is arithmetic. And yes, that is the same word as arithmetic. But when we put it in front of a word, it becomes an adjective, and we now pronounce it arithmetic. So this is an arithmetic sequence. An arithmetic sequence is a sequence that has addition or subtraction as its generator. That generator is called the common difference, and we usually call it just D for common difference. So any sequence that is generated by adding or subtracting each time the same value. So generator needs to be the same value each time. So in other words, that sequence we saw where first we added 1, then we added 3, then we added 5, that is not arithmetic. However, this one is, because we're adding -3. And this one is up here, because we were adding 2. As long as we're adding the same number every time, then it's arithmetic. So this one was arithmetic, as was this one here. Okay? Geometric is the other one. A geometric sequence has multiplication as its generator. Notice it does say or division, but we're really looking for multiplication. And we usually call it the common ratio. Some people might call it the multiplier. But common ratio, we usually use the letter R to refer to that common ratio. And again, it's got to be the same value every time. If we change the value that we're multiplying, it is no longer geometric. So it's got to be the same value each time. So on the other page, sequence B is geometric. So this one here was geometric because we were multiplying by 2 every time to get the next term. So, arithmetic. You generate it by adding the same number every time. That number is called D, the common difference. Common ratio is when it's geometric and we generate it by multiplying the same number every time. So, down here, another sequence A, 5, 10, 20, 40. Is this geometric or arithmetic? It is geometric. So on your Delta Math tonight, you are going to need to be able to distinguish between geometric and arithmetic, and you need to describe the generator. So you need to give the generator. Okay? Geometric. The generator is called a common ratio, so we use R. And what is it? Geometric means we're multiplying by the same number every time. What are we multiplying by? 2. Reason it's called a common ratio. A ratio is what you get when you divide two numbers. And look, if I divide 40 divided by 20, I get 2. 20 divided by 10, I get 2. 10 divided by 5, I get 2. There is a common ratio. Common means it's always the same, and it happens to be 2. So the common ratio means what do you get when you divide the two numbers next to each other? So geometric. R equals 2. Next one, sequence R, -2, -7, -12, -17. Arithmetic or geometric? It's one or the other. Yeah, this one is arithmetic. Arithmetic has a common difference. Common difference means it's what you get when you subtract two numbers next to each other. So if I do -17 minus -12, -12 minus -2, what do we get? -5. We're decreasing by 5, -5. So that's what common difference means. So like right here, my common difference is -3, because 7 minus 10 is -3. 4 minus 7 is -3. Up here, my common difference was 2. 7 minus 5 is 2. 5 minus 3 is 2. 3 minus 1 is 2. So common difference means what do you get when you subtract the two numbers that are next to each other. Okay? So we had geometric, arithmetic. And then our last one on this page, sequence F. 12, 4, 4/3, 4/9. Arithmetic or geometric? Yeah, it is geometric. Okay? If you're not sure, look at arithmetic. To be arithmetic, we would subtract 8, so add -8. Clearly, it cannot be arithmetic because if you keep adding or subtracting numbers, you're never going to get into fractions. The only way you get fractions is by multiplying and dividing, so it's not arithmetic. That makes it geometric. Which means we have a common ratio. That means there is a number that's being multiplied by here. But notice that these numbers are decreasing. What do you think we're multiplying by? Negative. Not negative, because when you multiply by negative, you get a negative. So it's a little tricky. What are we multiplying by here? Okay, what'd you say? 1/3. 1/3. It is. It's 1/3. Okay. When a geometric sequence decreases, it's because of division, which means you're multiplying by a fraction. So in other words, what do you do to the 12 to get a 4? You're dividing by 3. But we like to think of it as multiplying, so we're multiplying by 1/3. So dividing by 2, we're going to call it multiplying by half. Dividing by 4, we're going to call it multiplying by 1/4. So dividing by 3, we're multiplying by 1/3. So 1/3 of 12 is 4. 1/3 of 4 is 4/3. This literally fraction means 4 divided by 3. When you multiply by 1/3, you multiply the top number by 1, bottom number by 3. So that's how 4/3 becomes 4/9. Top number got multiplied by 1, bottom number gets multiplied by 3. That means my next one, if I kept going here, would be 4 over 27. Because the top number gets multiplied by 1, bottom number gets multiplied by 3. That's what 1/3 does when you multiply by 1/3. The top gets multiplied by 1, the bottom gets multiplied by 3. Okay, our last page here, we're going to look at some graphs. So here is a graph of a sequence. On the horizontal, we always put the term number. So term number 1, first term, second term, third term, etc. And then on the y-axis, that's basically the value. So the value of the term. So right here, first term has a value of 0. So when it says, what are the first 6 terms? Well, my first term is 0. My second term has a value of 3. My third term has a value of 6. And then 9. And I now run out of graphs, so I don't know what the next 2 are. Or do we? Can we figure out what kind of sequence this is? Yeah, arithmetic or geometric? Arithmetic. So this is arithmetic. And our common difference is 3. We're just adding 3. So yeah, I can figure out the next terms that are missing off of my graph. This would be 12. This would be 15. 1, 2, 3, 4, 5, 6 terms. So there are the first 6 terms of the sequence. Next, f of 15. This means, what's the 15th term? So f of 15 means, what's the 15th term? That's what it's asking for. Okay, so my 15th term. Well, I've got 6 here. I can keep going. Next would be 18, 21, 24, 27, 30, 33, 36, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14th term, and there it is. 15th term is 42. Now, do you guys think there's probably a more direct way to go than that? Yeah, we will talk about that later. Because what if it had said, what's the 123rd term? You probably do not want to sit there writing all those numbers out. So yes, there is a better way for us to do that. But 15th term, not so bad. We just went out 15 terms. Okay, so how do we go from one term to the next? So we add 3 to get the next term. That's because it's arithmetic. We already said that up there at the top. So arithmetic has a common difference. Okay, now let's take a look at this graph. When we graph a sequence, what we do not do is connect the points, okay? Because there's no numbers in between. The sequence is these numbers only, of course, dot, 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 it continues, but 2 is not in the sequence. If I connect these 2 dots right here, I'm including, hey, look, there's a time when the sequence is 2, there's a time when the sequence is 1, and that is not true. So in other words, I go from 0, I skip all the way up to 3, and then to 6, then to 9, then to 12, so do not connect them because there's no values in between. However, look at those points. If we did connect them, what kind of shape do you think we would get? You notice something about these points? For example, hey, this is 3, that's 1. If I look between those 2 points, that's 3, and that's 1. If I look between these 2 points, that measures 3, that measures 1. So what do you notice about these points? If we connected them, which we're not going to do, but if we did, what kind of shape would we see? Okay, shape that we're very familiar with. We did a whole chapter on it. And then we did a whole second chapter with 2 of them. It's a line. Okay, I connected them. It's a line. Of course, we're not supposed to connect them, but it is linear. So they do still form a linear pattern. So how does the graph change from one term to the next? So it has the same rate of change. Remember, rate of change is the slope. And it happens to be 3. And the graph has a linear pattern. And that will always be true with an arithmetic sequence. If you graph them, it'll be linear. The points will line up. We won't connect them, but they still will line up with the same rate of change. This rate of change here is 3 over 1. The rate of change here is 3 over 1. The rate of change here is 3 over 1. The rate of change will stay the same. It'll be 3 or 3 over 1 because the graph will be linear. Okay, example 4. The sequence is not written there, so right up here I'm going to write sequence B is 1, 4, 16, 64, ... You kind of need that information to do the problem. When it says consider the sequence and there's no sequence, it's kind of hard. So, part A, if that's our sequence, how do we go from one term to the next? So what's going on here? Yeah. Multiply by 4. Okay, so that makes this geometric. So this one, I'll write it over here because there's not a lot of room over there. So this is geometric with a common ratio of 4, just so that we know. We're multiplying by 4, so this is going to be geometric with a common ratio of 4. Part B. This is another way. B sub 8 means what's the 8th term? 1, 2, 3, 4. I'm going to use a calculator because these are going to get big really quickly. Because my next term, 64 times 4, is 256. And then I hit times 4, and I get 1,024. And then I get 4,096. And then we get 16,384. 1, 2, 3, 4, 5, 6, 7, 8. So there is term number 8. B of 10. That's just the other notation, function notation, but it still means what's the 10th term. So I'm going to keep going. My next term is 65, 5, 36. That's my 9th term. Multiply by 4 again. 262, 144. My 10th term is 262,144. Notice that geometric sequences, when you're multiplying by a number, not a fraction, but when it's increasing, it's going to increase super fast. 10th term, we're at, almost 300,000 versus the arithmetic over here. 15th term, we were only at 42. So do notice that geometric grows super fast. Okay, we're going to graph the terms of the sequence. So the ones that fit on this graph. So first term is 1. So down here, my first term is 1. That's 20. That's 10. Halfway there would be 5, so 1 is very close to the bottom there. It's not on 0, but it's very close. My second term was 4. So here's 10. Halfway up to that first line would be 5, so 4 would be...
The bell.
Oh, did the bell supposed to ring? Okay. So... put the rest of those on there. That's all that we were missing, and you can turn that in. The Delta math tonight is what kind of sequence is it? Arithmetic, geometric, what's the common ratio, what's the common difference? So exactly what we just covered in the notes there. So I'm just going to go ahead and finish this up. notice that these points curve and they get really big really fast. So there's 64 and we're way up here. Okay.